Hello, I'm Dr. Thomas Blaine, Associate Professor with Ohio State University Extension. And today on Earth is Our Home, I'm going to be talking about why it's so difficult to predict future temperatures and climate. So stay tuned.
Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. He's a Extension OSU Associate Professor with The Ohio State University. And today we're going to be talking about some interesting things. Why is it so difficult to predict global warming? Tom, it's always a pleasure talking with you. I really learn a great deal from you.
It's a pleasure being here, Patrick, and I want to extend my thanks to OSU South Centers, specifically to you and Sarah Swanson for having me do the series. It's really a great experience, and I hope that the viewers are learning quite a lot from it.
I'm really a cynic when it comes to global warming, global climate change, because I grew up in a time where we question just about everything. And, you know, in preparation for today's program, I wanted to throw something out to you. You know, Tom, there are 249 countries, of which 194 are independent, you know, in the world. Only 170 countries have policies that address climate change. And you know that as well. And only 2 countries are meeting their climate pledges. You know, I had a chance with different websites, especially on pbs.org. They demonstrated that there are top 10 global emitters of carbon dioxide. And you can see on the screen how much metric tons each country throws out. It ranges from anywhere from 25 million metric tons to 0.61 metric tons. Each country appears also to be working on global change differently. And this is what I found. Some countries do this, some countries say that, some countries go to a different direction. And I'll be quite honest with you, Tom, no wonder everyone is confused about global climate and global change. There is not one specific area or direction we seem to be going.
Well, you're right, Patrick. I mean, each country is basically pursuing its own interests, if you think about it. And some countries find it in their interest to pursue energy that's a little bit cleaner than others. Other countries might be just struggling to survive. I did write, I know that we've posted on my fact sheets, we posted down at the bottom of some of these videos, the update 2020 fact sheet. And I'd like to post that again. I encourage people to read it. But when you read that update 2020 fact sheet, in the very early part of it, there's a link to the 1996 fact sheet that I did. We've kept that online and it's clickable in the 2020 because I wanted people to see what I wrote a quarter century ago, what I was predicting, because I predicted this. I mean, exactly what you're talking about is written down in that 1996 fact sheet, that countries would probably not, almost certainly not. And I use pretty strong language. I encourage readers to go look at it. And I hope we put that link underneath here to the 2020 fact sheet, because I did predict that this would happen, that the different countries would not be able to get on the same page And I wasn't very hopeful that the world would be able to come together to keep CO2 emissions down, to prevent CO2 concentrations from continuing on their trajectory. And I've been right. I've shown you all the curve that shows the CO2 concentrations in the atmosphere going back all the way to 1960. And it doesn't show deviation from the trend. Now, last episode, we talked about Svante Arrhenius and the 19th century scientists who first came up with the idea of global warming and actually tried to measure and did measure what various amounts of CO2 concentration in the atmosphere would do to temperature. So for any given amount of CO2 increase, what does that do to global temperature? And we're going to review those results today. Again, we're going to look at Arrhenius's results from the 1890s, about 130 years ago, and talk a little bit about modeling today. You may recall that Arrhenius greatly overestimated the amount that the temperature increase. He greatly overestimated the amount of temperature increase that would come about as a result of CO2 increase. And it's a good thing at that, because if we were at the temperatures he predicted in the 1890s, if we had reached those temperatures now, we probably wouldn't be having this conversation, because Earth would be pretty well devastated. And we were talking about why was he off so much, and the fact that our understanding of the climate system has increased a lot. We know more about the environment now and CO2 precisely because of the work of Arrhenius and the other 19th century scientists that we talked about, John Tyndall, Claude Pouillet, all these scientists and scientists since then who have been working on this. But I want to just talk about why, when you hear about some of these projections, why it's so difficult to project out. First of all, we've already studied in a lot of early episodes, and I encourage you to go back and look at those episodes. They're on the playlist. Go back and look at those where we talked about Earth's climate engine, how it works. We started out with a real neat flow in Hadley cells, Ferrel cells, and polar cells, the trade winds, the prevailing westerlies, the polar easterlies, the subtropical jet, the polar jet. We did all that. We derived why all those things do what they do. But then we saw that when you throw in the rotation of the Earth, when you throw in the fact that there are huge land masses adjacent to huge oceans, and land and water take up heat at a completely different rate, you get differential rates of warming, and that causes movement of air, otherwise known as wind. Some of those winds run counter to the global flow that we derived initially, and that produces chaos. The Earth's climate engine contains elements of chaos. It's a chaotic system. There are patterns. We see patterns of high, low pressures. We see all kinds of patterns to the climate, but it's still chaotic. Trying to figure out where a high pressure system is going to be even in 2 weeks. You look at your weather forecast and it's like further out you go, the less certain the forecasters are about what they're predicting. It's because there's elements of chaos in the system. The second reason, as far as predicting future climate, is the presence and magnitude of feedback loops. So I want to talk about those. First of all, the chaotic elements. We learned all those basic models, how the flow was nice and orderly in Farrell cells and Hadley cells. Please go back and look at that. Then we had the rug pulled out from under us by finding out that, wow, because of uneven heating and everything with high and low pressure systems, they have their own circulation. We talked about the Coriolis effect and how it drives circulation around high pressure systems clockwise in the northern hemisphere, counterclockwise in the southern hemisphere, and then low pressure systems go counterclockwise in the north, clockwise in the south. That changes the flow of winds from those prevailing westerlies and so forth. The trade winds all get changed because of that. We talked about the presence of El Nino and La Nina, the southern oscillation. If a high pressure system just happens to set up in one side of the equatorial Pacific versus the other, it has enormous, that's the southern oscillation. When, it sets up in the west, it drives warm water across the equatorial Pacific. The entire equatorial Pacific warms up. That's El Nino. It changes Earth's temperatures and climate. We went through that. When the high pressure sets up off the coast of South America, it drives cold water out. Temperature of the equatorial Pacific drops, changing global weather patterns. Again, chaotic elements, okay? They influence Earth's temperature and Earth's climate. Feedbacks are another one, I would say the second one here. We've talked about how when you add CO2 to the atmosphere, the molecules of CO2 physically block the movement of heat that's reflected from Earth's surface that's moving toward space. The heat, the infrared energy, literally gets blocked by CO2. If we didn't have that effect, Earth would be a snowball. But we're putting more and more of the CO2 in to the atmosphere, causing warming. But the thing about it is, it doesn't stop there. You get what's called a feedback. When you make a change to a system and it causes a result, but then that result causes something else to change that influences the result, it's going back that way. That's a feedback. So when you warm the surface of planet Earth, you get more evaporation from the oceans. That means more water vapor in the atmosphere, but water vapor, like CO2, is a greenhouse gas. It traps a lot of heat. And so that's a positive feedback. There are other things, the clouds themselves. The top of the clouds are white, and they reflect heat back, ultraviolet. They reflect the ultraviolet rays back into space and prevent sunlight from warming the planet. On the other hand, they trap heat down below the level of the clouds and contribute to warming. So which one weighs out on that? Depends on the type of clouds, for one thing. Cirrus clouds and cumulus clouds have different kinds of effects, but they complicate things. There are other feedbacks, okay? And not just the tops of clouds that are white, snow and ice. There's an enormous amount of planet Earth that is covered by white surfaces. Antarctica, the Arctic Ocean. We've talked about how the poles are Earth's air conditioners. They reflect sunlight, leading to cooling. If we melt that ice through warming, we uncover dark surfaces that then retain heat, leading to warming. Again, that's a positive feedback. It's hard to model. Another wild card is methane. We talked a little bit about that, CH4. There's a lot of methane trapped under permafrost and the sediments of the oceans. As we warm, we release more methane, and that causes more warming in turn. Very difficult to model. All these changes, it's extremely difficult to predict how much each one of these feedbacks will kick in. So we can't really hold Svante Arrhenius liable for overestimating the amount of warming, when he did his first study on this in the 1890s. I just want to review that again. He calculated what temperatures would be if you took the CO2 level in the atmosphere where he was. He did it for 67%, like if you cut it, 33%. How much would the Earth cool? Then if you went up by 50%, 1.5 times what his level was, and his level was about 280 parts per million. That's where we are now, it turns out. What would happen if it doubled, tripled, 3.5? And if he did it for each location on Earth every 10 degrees latitude, from 60 between 60 and 70 degrees south to 60 to 70 degrees north. And he did it for each season. And I want to just review, if you don't like centigrade, and most of us don't, that's the first row. So basically, Arrhenius predicted temperatures based on the CO2 that we're very close to now, that essentially the annual average increase in temperature at this latitude would be about 6.3 degrees Fahrenheit. That's the one way out there to the right, the annual average. You can see he predicted the greatest temperature increases would be in the cold months, December through February, March through May. And the least amount of warming would occur in the warm months, 5.9 degrees. Now, we know, we've discussed a lot, the temperature increase has been 1.8 degrees Fahrenheit. 1.8 degrees Fahrenheit. So, I mean, he's overestimated by more than a factor of 3, I guess, 3.5 or so. He didn't have complex computer models with all these feedbacks and things. He was a leading scientist. He got the Nobel Prize, not for this work, but for other work. That's how great a scientist he was. But, he didn't have the complicated climate models we have today. And I want to point out, I did mention this last time, over or underestimation are common occurrences when a science is in its infancy, when a science is in its infancy. So the Andromeda Galaxy, when astronomers first figured out it wasn't a body inside our galaxy like the other stars, it's a galaxy in its own right with hundreds of billions of stars in it, just like the Milky Way. They went about immediately trying to measure the distance. That became a big, big thing. And the early estimates were about 500,000 light years, 500,000 light years. And they were pretty content that they had measured that right. Well, they didn't have the data, the instruments, the understanding of stars and brightness that we have now. Now we have very precise estimates that are telling us it's 2.5 billion light years. So that's a factor of 5. okay, that they were off in the early days. And that's actually even slightly more than Arrhenius's error. And, science is self-correcting. You start out doing some inquiry, you get some results, people look at that, and then they might see that, oh, wait a minute, this technique might be more accurate. And it's a self-correcting thing where the knowledge grows. It's not static. It's not based on faith or something like that. It's based on evidence and reason. So now we have very good measures that show the distance. And we also are getting better at predicting, future climate. So here's an example. We saw that Arrhenius had measured 6.3 degrees Fahrenheit in Ohio. And if it were like that, we would not have the kinds of agriculture we have in Ohio. It would be, Ohio would be a very miserable place to be right now because of other factors that would accompany that 6.5 degree increase. Okay, so how far have we come? Let's look at a recent example. Jet Propulsion Laboratory at NASA, they ran a model of a composite group of studies they called an ensemble. They did a hindcast. They looked at temperatures from 1970 to 2000 with the model they had that predicts all these impacts on temperatures. And then they did a forecast from 2001 to 2020. And let's look at their model accuracy here. All right, there you go. The dark line, those are, and the dark line in the middle, those are the projections. The dark line. The red line are the actual temperature observations from 1970 to 2020. As you can see, 1970 to 2000, they already had the data in there. And they ran the model over top of that data to duplicate it. And then you look, and they didn't use the data for 2001 to 2020. They didn't use that data. They went ahead and used the model to predict, given what circumstances were in that era, what the temperature should have done. And as you can see, it traces very well. The shaded area are confidence intervals. When you hear there's a presidential poll or something and so-and-so's ahead by 3.5 points, but the margin of error is 6 points or 3 points or 2. Those are margins of error, those shaded areas, which tells you that margin of error, for like 2020, it could be as low as a 0 degree increase all the way up to about a 1.8 degree. That's quite a wide confidence interval. Why? Well, we just talked about that. It's very difficult because of all the unknowns. And one of the things you might want to notice is the observations have more annual fluctuations to them than the actual predictions. The predictions tend to show fairly straight because they're not capable of taking into account the effects of like an El Nino. I mean, in 2004, when they were predicting this, they couldn't tell that in 2016, where you see the temperature goes way up above the line, see where the red line bounces way up at 2016. That was one of the strongest El Ninos ever. And in 2004, they didn't know that would happen, but they did predict that the temperature would be significantly warmer than it was in 2004. And so I think this graph shows we've come a long way since Arrhenius. But we've still got a long way to go, because when we talk about predicting out to 2050 or to 2100, and we will get to that one day soon, there's quite a bit of that very large confidence interval. That means there's a lot of uncertainty.
There does appear to be a lot of uncertainty. We're talking with Dr. Thomas Blaine. Dr. Thomas Blaine is a OSU, Ohio State University Extension Associate Professor. And Tom, again, I can't thank you enough for all the information that you've given us.
You're sure welcome, Patrick. Thanks for having me.